in Module 7, we're going to talk about leverage and influence and linear regression. And this will be the final topic for this course. And so let's get right to it. And there's another required reading or supplemental reading to go along with this lecture. It's just like a technical report. It's available on the internet by D.C. Hoagland and R.E. Welsh, called The Hat Matrix in Regression and ANOVA from 1977. And so I recommend you read this technical report. Okay, and so throughout our example problems, we've been pointing out certain data points that were interesting, and some that were, for example, influencing the regression fit. In fact, from the jackknife resampling, we once in a while we would find that the shape of the regression fit would change significantly if one of the data points was left out of the training set. And so now we're going to explore the mathematical reason why some certain data points are more influential than others and least squares regressions. And the issue arises that the ordinary least squares algorithm that we derived through the minimization of the residual sum of squares equation, that it does not equally weight the data points used in the regression. And so there are two types of points that have a greater importance to the regression. The first one are outliers, and we've been sort of, throughout the whole course, I've been pointing out certain outliers. And an outlier is a dependent variable datum, so it's a Y data point that has a large magnitude deviation from the sample mean. And so remember, the first thing we do when we collect the data, we calculate those sample statistics, sample mean, variance, things like that. And so, many times we'll have an underlying function, so there will be, a Y min and a Y max. And so the outliers tend to be those Y, but still your sample data will have a mean. And remember, the zeroth order model is, or the simplest model that you can try to fit is Y equals beta naught, which will equal the sample mean if you use least squares regression. And so the outlier is just a dependent variable datum, or a Y with a large magnitude deviation from the sample mean. Now the term outlier has a sort of a negative connotation, meaning, oh, it's a bad data point. That is not true. Okay, so an outlier is not a bad data point. Now, some bad data points are outliers, but an outlier is just a Y variable that has a large magnitude deviation from the mean. So that's an outlier. And then now data points near the boundary of the input space, and those are outlying predictors. Remember, the X, we sometimes call the independent variable a predictor. And so outlying predictors, the variables that are at the boundary of your input space, they can have greater influence on the model prediction as well. In the previous lecture, we briefly went over bootstrapping, and the model influence can be so great that the bootstrapping methods are also affected because that bootstrapping is using the original regression. And so we had introduced a few lectures ago the hat matrix, and so the hat matrix actually gives the quantitative measure of each data point's influence on the fit. And so we're going to explore the hat matrix in more detail in this lecture. And so just remember, when I say an outlier is it's a Y, it's an the output value that has a large magnitude deviation from the sample mean. And then an outlying predictor is an input location near the boundary of the input space. And so here's our equation, the least squares regression algorithm, the solving for our linear model coefficients beta. And then when we make a model prediction, and when we do our cross-validation, we always have to do residual analysis, so we have to evaluate our regression model at the input locations. And so we have to obtain the y-hats, which is basically the model predictions at the input locations. And so that is then just our X matrix again times beta. But if we substitute in the original definition of beta, we now get the X matrix times the X transpose of X, the inverse. So the X transpose X is a new matrix. It's a symmetric matrix. We take the inverse times X transpose times Y. And so we define the hat matrix, or it's sometimes called the projection matrix. H equals this X times the inverse of X transpose X times X transpose. And so what's interesting is this hat matrix, the H, the hat matrix, is only a function of the sample inputs and then the chosen regression functions used in the regression. So the hat matrix is independent of the output values Y. So the hat matrix is independent of Y. And so, but if you look at this matrix, basically you have a vector of Y's going to be multiplied by, so basically you have a column vector of Y is going to be basically, when you do the vector and matrix math, it's the dot product of the vector Y with each row of the hat matrix. And so each Y bar is a linear, so each Y bar model prediction, it's a linear combination of your output values Y's in your data set. And so the model predictions Y hat are a linear combinations of the sample output Y. And what is a linear combination? A linear combination is essentially, it's a weighted average. And so each Y hat, so Y hat I is a weighted average of the output vector Y with the weights given by the row I entries of the hat matrix. And we'll show that in the next slides. And so in the model prediction mode, it's a weighted average of your sample data. And so and that's why I actually even consider linear least squares regression is also it's a type of data smoothing. Now, but generally, now in practice, once we calculate the coefficients, we usually will tend to like throw away this matrix and the Y, and we'll just use the betas in our regression model, in our regression functions. But when you fully expand it out, yeah, each prediction is a weighted average of the outputs in your training set. And so let's look at some additional properties of the hat matrix. And so the diagonal entries of the hat matrix, I'm going to designate HII, they define what's called the leverage of point YI on the model prediction Y hat of I. And so, and when we look at the hat matrices, the sum of the diagonal entries, which is actually the trace of the matrix, so the trace of H equals P, which is the number of parameters in the model. And I think we're going to do a simple linear model, and you'll see that the trace of our hat matrix sums the two. And the sum of each row or the column equals 1, which basically means that the weights used in the weighted average are properly normalized. That's just another property. So I just told you qualitatively that this YI is this weighted average, and because it's Y, it's a dot product of this Y vector with each row, and it turns out that if you sum the elements of each row, they sum up to 1. That just says the weights are normalized to 1, which we normally do in weighted averages anyways. You want your sum of your weights to equal 1. And I'll show you this in the example coming up next. And so each HII is bounded between greater than 0 and less than 1, and the leverage, and so basically the Y hat is basically the summation of HIK times the Y of K. And then remember, our Y's are our observed output data from our training set. And so the model prediction is basically, it's a weighted average of these of these output values. And also what's interesting is that the partial derivative of the y hat with respect to the actual observed data point yi, it equals hii, the diagonal entries of the hat matrix. Once again, so that the derivative of y hat is independent of the actual value of yi or y hat. Yeah, so the weight hii is independent of the magnitude of y. And so the influence of the data point yi on the prediction of y hat of I is the deviation of yi from the sample mean times hii. And so in some cases, we might have an outlier, but if the hii is a small number, then that data point doesn't affect the regression fit. But sometimes it does not have influence on the regression if hii is small. And so now I think it's best, let's do an example. And we're going to do another simple linear model, but just to really emphasize the properties of the hatch matrix, we've done a different data set. And we're still sampling from the y equals 1.5x, and I'm using variance of 0.5. So I'm using a greater variance for this particular problem. And I'm using, if you want to generate this data set, here's the MATLAB script that I use to actually create these 10 data points. And so first, I did 10 evenly spaced points between 0.1 and 1. Okay, first I set the random seed to 35,680. Set the random seed. I made 10 evenly spaced points. But then now, so we have all the data points basically between 0 and 1, but then I actually wanted a data point near the other boundary, so what I did was I just replaced the very first data point with 0.7, negative 0.7. So we created a vector, but instead of having a data point at 0, there's no data, I replaced the 0 data point with the negative 0.7. And then I sampled 10 using the rand command. I did my 10 random numbers that are normally distributed with a 0.5 standard deviation or 0.25 variance. So you're able to generate this exact data set if you want. And so when we do the line of best fit or the simple linear model, also to show you the x bar, y bar, the line of best fit, the blue line, falls right in the, passes through the mean point again. And so the line of best fit is negative 1.0012x plus then negative 0.11427. And our generating function was negative 1.5x. And so we have a pretty big, about a 33% deviation on the slope. But of course, once again, it's a small data set. And also what we're going to see is this data point is going to be highly influential. And if you just look at it, this particular data point, the one at negative 0.7, it happened to have a negative noise of about, it would be 0.25 or 0.3 of negative 0.3. And so, yeah, that's less than half of a standard deviation of magnitude. But this one data point happened to have a negative random noise component. And so we're going to look at these 10 data points. And I think I've arranged them. This is data point 1, and then they go kind of in order 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, I guess there was 11 data points, and then the first data point I changed to the 0.7. And so these all go in 0.1 from 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1. And so for hat matrix analysis, and I would encourage you to do this with your data sets. It's another, in fact, I generally don't do jackknifing because usually you can just once you get some experience, you can often just tell which data points are influential, but you can do it quantitatively with the hat matrix. So actually, make the hat matrix and look at it. And so this is a printout, I think, from the MATLAB command window, or from the variable window. And so this is the actual hat matrix. So this is the data set, and for a simple linear regression model, so I'm actually showing you this is the hat matrix. And yeah, just I have some indexes here for you. So row 1 is -0.7, row 2 is 0.1. We're going in 0.1 increments down to 1. Okay, and then of course, same along the row levels. And first, I want you to look at the diagonal entries of this matrix. Okay? And if you notice, for our -0.7 data point, it's 0.666. And then it's 0.14, 0.11, 0.09, 0.09, 0.09, 0.1, 0.12, 0.14, 0.18, 0.23. And so most of the data points, most of these data points have about a 0.1, 0.12 HII. And this one has 0.66. Now these two also had almost what, 0.2? Now yeah, 0.18 and 0.23. And so the data points at the boundaries have significantly higher diagonal entry values. In fact, if we do the average HII is 2 divided by 11, which is 0.1818. So we have a large subset that are less than the average. Now this one is a factor of 3 higher than the average. Or it's actually 3.66 times the average. And basically, that's what you do when you make your hat matrix. Calculate your average HII, and then basically kind of a rule of thumb is if any individual HII is large, meaning if HII is greater than 2 times P divided by N, in this case P equals 2, that means that the HII is large and that data point will have high leverage. And so let's look at this in a little bit more detail. So now I've just plotted what we had before from the, this is just all of them plotted this is the trace of the H. And the trace of H is the sum of the diagonal entries, and you can confirm this yourself. All of these 11 numbers add up to 2. Yeah, and so in this data set, that negative 0.7 data point is a really significant data point in that regression, and also these last 2 data points has higher influence. And that is the primary reason why the slope is, the magnitude of the slope is significantly underestimated, because this one had a negative noise. And so it basically it drew the regression fit down. Okay. And so yeah, just some other comments. Remember, the line of best fit determined from least squares must pass through the point x, y bar, the sample means of the inputs and outputs. And so if a sample input xi equals x bar, it happens to land right on the sample mean, or it's just close to x bar, the fit is almost independent of the data pair xi, yi. And so the line of best fit has to pass through. In fact, right here we have a data point. In fact, we have 1, 2, 3. The 3 closest, these 3 data points, they all have positive noise, but basically the fit is constrained to pass through the sample mean, despite having the closest 2 data points has the positive noise. So the fit in this local area is unaffected by these data points, because the fit at this location is determined by the sample statistics of the data set. And so the data points near X bar, so if you have a cluster of data points near X bar for the simple linear model, they have small influence. The only influence they have on the regression is what their individual contributions to the Y bar. And so if you have n data points in a data set, their contribution to y bar is just 1 over n. That's the weight. And so the least square solution is not very sensitive to the outliers in the vicinity of x bar. And so let's do another example problem. Okay, just remember what's our original line? It's all right. So it's the slope beta 1 is negative 1.0012. Beta naught is negative 0.11427. Here we're adding a new data point, okay, at x bar. I've added a new data point. I think it's 2 standard deviations. I think it has a +1. I've added a plus or minus 2 noise added to x bar. And so if you look, the slope, so we've added a new data point, but the lineup, the slope is remaining exactly the same, negative 1.0012, but now it's shifted the y-intercept. And so this is an extreme outlier. Okay, so 4 standard deviations. And so the only influence this data point had on is its influence on the sample mean, which just shifted the whole curve up slightly. Because it's only one data point, and actually did not change the slope at all. Only had a small change in the y-intercept. And now here, we've done the same thing, but it's negative 2. We've added, it's 1.5 times the x bar, negative 1.5 times the x bar minus 2. So now we have an outlier on the other part. The slope is staying the same, but all it did, you look at it relative to the actual underlying function. Now it's just shifted, not very much, it's just shifted it down a little bit. And so in this case, what's interesting is you can have even an extreme outlier, but if it's near the actual sample mean, it's not going to have, it'll have minimal influence on the actual regression fit. Only as much as it influences the value of the y bar. And so let's do now with those extra data points added. And so this is the hat matrix for the additional, we've added the 12th data point. Its x value is 0.436, the sample mean. But look at the weight, look at the row 12. It's 0.0833, 0.0833, 0.0833. They're all the same weights, and that's 1 divided by 12 actually. And so that goes back to, so y hat of I equals the summation from 1 to n of hik times y of k. And so the y hat, that is just showing you, now you have your vector of y's dot product with this vector. It's just the sample mean of the y's. And so the y hat at x bar of 0.436 is the sample mean, and that comes out of the hat matrix analysis. And that actually is showing you why the line of best fit always passes through the sample mean. You can actually see that in the hat matrix analysis. And so, yeah, I generally, if I'm doing a linear regression model, I'll usually, if you want to know the actual, the leverage, you should look at, especially if you're interested in a certain region of your input space, you can look at your, the weights of the data points in that region. And I think that is it for this lecture.